Dear students, welcome to lecture number 7. In lecture number 6, you know that we have discussed what are the important or basic assumptions which we have to take into consideration while using the limit state methodology for analysis and design of RCC structures. So today this lecture is very important, lecture number 7, and where we will be going to discuss again in continuation to limit state design as per IS 456 2000. Today's topic will be the design analysis, that means how we do the analysis and how we differentiate it from design of RCC section, RCC beam particularly. So when a beam is subjected to loading, then what will be its behavior under flexure, and what are the design parameters we have to consider while doing the analysis as well as subsequently in the design of the RCC beams. So that's why now you are able to see that we are talking about two things, that is, one is analysis and other is design. Now reinforced concrete frame structure, you may have seen that first of all there will be a creation of a frame structure. Earlier times we were using load bearing structures, so now we are switching over to frame structure. So let us first of all understand what is the meaning of frame and how it look like. So you can see a picture which is of RC frame structure, and there are various components of the structure. If we start from the bottom, then from this sketch we can able to understand that lowest portion is the foundation. So foundation is one element or one component of the structure, and above this foundation you will be able to see that some column type of structures are there. So they are vertical members which are generally considered to be under compression. So they are vertical member, these are columns, and after that you can see that there is one horizontal member which is supported by column. So that member is generally called as beam. And above the beams, above the structure of these various number of beams, slab is supported. So another component is slab, and similarly there are various number of columns, beams, slabs as well as foundation part. So that ultimate goal of designing a structure or constructing a structure is, so whatever be the superstructure, that load can be easily transferred to the substructure part and ultimately to the soil safely. So let us just go through the definition part. A RC frame structure generally consists of various structural components or members such as beams, column, slab and foundation, which we can easily see in the diagram, as well as can easily understand that what is the meaning of foundation, beam, slab and as well as column. Now in general, a reinforced concrete beam, also termed as RCC, in a very common language we say RCC. So RCC means reinforced cement concrete. So cement is one of the component of concrete that will be having the binding properties. So any term you can, if you are replacing cement, so accordingly the terminology may change, but in general we will talk RCC beam. And a very important aspect of beam is primarily it is subjected to flexure. Flexure means bending, and it is supporting the slab. So as you know that if there is a column structure, column is generally considered as a compression member. It will be subjected to compressive stresses, compressive forces, and depending upon the location of the load, whether it is along the axis of the column or it has some eccentricity, so accordingly there may be some bending may also occur. And in case of RCC beam, we generally consider that it will be subjected to bending, that is, it will be under flexure. So that's a very important aspect of today's lecture, is that we have to discuss the behavior of any beam under flexure. Similarly, beams, because slabs are supported above the beam, so beam will be acting as a support to the slab, and slabs are also generally or predominantly we can say it is subjected to flexure, it is subjected to bending. Column and walls may be subjected to flexure, and as I already illustrated, that if there is any eccentric type of load or any lateral pressure is acting on the columns or the walls, some bending may be happen. So that means they may be subjected to some flexure also. Otherwise, they are in general considered as column, considered as a compression member. Now, beams support the loads which is due to the slabs which it support, as well as their own self weight and other forces which may be like any internal movement, any shear, bending, etc. So various type of effects on a beam can be considered depending on the loading pattern. That means what type of load it is supporting, what pattern of load it is supporting. Now let us first of all try to understand what is the meaning of analysis and what is the meaning of design. So when we are talking about the term, or we are referring term analysis of a member, analysis of a structure, so basically what is the purpose analysis? So analysis refer to the evaluation or calculation or estimating the capacity of a structural member to resist the effect of various loads or movements to which it may be subjected based on its geometry. That means what is the cross-section dimensions, what is the length, etc., span. So what are the geometry of that particular member, and from which material it is made up of, whether it is of concrete of grade M20, M30, etc., or it is made up of a high strength concrete. So accordingly, based on the geometrical dimensions as well as the material type, material properties, we will be able to analyze that when some particular set of loading is acting on the member, so what will be the effect of those loads, just as movements as well as shear force, etc. So that capacity of the member to resist, whether it is able to resist or not. So all these information we can get by doing the analysis of the structural member or particularly structure. So for analysis you can refer IS code have mentioned some of the guidelines. That means what are the various methods of analysis which you can refer. Now let us briefly discuss about what is the meaning of design, so that we should never get confused in the meaning of the design. So design means working out the depth, breadth, etc. That means to work out what are the dimensions of the cross section of the member, and reinforcement details which we are going to use in case of RCC structure. So reinforcement details for the member to safely and economically resist the external applied load. So purpose of design is, very first is, it is the safety of the structure. in throughout its life, as well as when you are going to do the design. So your design must be economical. It should be economical. We can say it must be safe and it should be economical whenever any external loads are acting on it. So this is the difference between the analysis and design. In design part, we are working out the dimensions as well as deciding the material, and in analysis what we are doing, we are checking the capacity. So during the design of any RCC structure, we will be doing some of the calculation related to the design aspect and some of the calculation we will be doing towards the analysis. So they will uh, be going simultaneously one by one. Now let us understand very clearly and very patiently. So what will be the behavior of the RCC beam under bending, or in more technical language we can say in flexure. Now to understand the behavior of the beam before designing. So before designing we have to understand the behavior, that how it will be behaving when some load will be coming on, or load in the form of, it may be compressive load, or it may be tensile load, and it may be any type of movements, torsional effect, whatever be. So let us consider that a RCC beam, or RC beam you can say, is subjected to transverse loading, and the load is gradually increased in magnitude until the beam fails. So we are assuming for our understanding that there is a RCC beam which is subjected to transverse load, and we are increasing the load gradually in magnitude till the beam member get failed. So how will be the behavior, how the beam section will behave before its failure? So that we want to understand today. Now whenever any beam is subjected to transverse load, which we are going to increase gradually, so beam will go through very important three stages before any type of collapse. So what are these three stages? That we have to understand it more clearly. Then we can understand the mechanism of the RCC structures. So very first is uncracked concrete stage. You have to keep in mind that concrete is prone to cracks, or concrete may have some porosity. So first of all, when we are taking into consideration any RCC beam section which is subjected to loading, so it will be going through three stages before finally it getting collapsed. So very first stage is uncracked concrete stage. We will elaborate in the details. And the second stage is concrete is getting cracked, but in elastic stasis stage. And very third stage is ultimate strength stage. So we have to differentiate all these three stages carefully so that we can understand the mechanism how the RCC section will behave. Now let us go one by one. Very first is uncracked concrete stage. Uncracked concrete stage. So definition part or elaboration: at small loads, as we have already told that we are increasing the load gradually. So when the load magnitude is small, so at small loads, when the tensile stresses which are developing in the member are less than the modulus of rupture. Now what is the modulus of rupture? The bending tensile stress at which the concrete actually begin to crack. So when you are increasing the load, what is going to happen? Tensile stresses will be increasing. But till the tensile stresses are less than modulus of rupture, we can say the entire cross section of the beam is resisting the bending, with compression on one side and tension on the other side. So what we want to say here, that a member is made up of concrete, And as you start applying the loads, what will happen? Some tensile stresses will develop, some compressive stresses will develop. And before reaching the modulus of rupture stage, when your tensile stresses are lesser than modulus of rupture stage, then whole of the cross section of the beam will be resisting the bending effect and one side compression. That means above the neutral axis. Later on we will discuss the neutral axis, compression on one side and tension on the other side. Now you can refer this diagram carefully. Now here what we have taken a sketch or a diagram, a rectangle member. This is the cross section of a rectangular RCC beam, and this gray portion is it indicates concrete basically, and these circles indicates the reinforcement, steel reinforcement, and this dotted line in the middle of the section is the neutral axis. And in the previous lecture we have gone through the details what is the meaning of neutral axis. You can refer if you have any doubt. Now this is the strain diagram. Now how strain occur? Now we are talking about the uncracked concrete stage. So in uncracked concrete stage, epsilon C is the maximum strain in compression, because upper side of the section it is compression. Here this portion will be in the tension. So strain here will be compression, compressive strain, and strain below the neutral axis, you can say strain is getting increased with the uh, distance increasing from the neutral axis. And at the topmost fiber there is compressive strain, and the bottommost fiber there will be the epsilon C in tension. So compression as well as tension. So that's why we are we have discussed that entire cross section of beam is resisting bending with compressive stresses on one side and tensile stresses on the other side. And some of the stresses will be taken care of by steel, but they are not prominently considered here. Now, second type of section behavior is cracked concrete in elastic stresses range within the elastic limit. So as the loads we are going to increase, when you increase the load beyond the modulus of rupture, so what will happen? Cracks will begin to develop in the bottom of the beam. Bottom of the beam means below the neutral axis, and the movement developed at these loads. When some load is applied, it will create some movements. So when your load is beyond this limit, modulus of rupture, then the movement which are getting developed at that load, when the tensile stresses in the bottom of the beam equal to the modulus of rupture. So when they have reached modulus of rupture, and it terms as cracking movement. So that movement which is at the level of modulus of rupture, that movement is termed as cracking movement, MCR. Now you can understand it more effectively in this diagram. Now you can see here we have taken a beam, and it is simply supported beam, and some load may be acting from the top. That means transverse load is acting. Accordingly, we have drawn a movement diagram, that is the bending moment diagram. So you can see here at the level of when your movement is reaching up to cracking movement, so within that range you can see some cracks are getting developed. So these cracks are due to this movement. That means these are the flexural type of cracks which you can consider. Now if you still go on increasing the load, on further increasing the load intensity, the movement will become greater than the cracking movement. So here M will be more than MCR, and then what will happen? Crack will quickly spread up to the concrete surrounding the neutral axis. So now if there is suppose neutral axis, then these cracks will start developing in the upside. That means from the bottommost fiber of the concrete member, and towards the, that means cracks will start propagating towards the neutral axis, and the neutral axis begin to move upward. So later on you will be able to understand what is the meaning of this neutral axis movement. So at this time we are able to understand that when you are increasing the load, and accordingly movement will develop, and as soon as the movement reaches to the cracking movement, some cracks will develop at the bottom of the member. That means due to the tensile stresses developed, and further as you increase the load intensity, accordingly the movement value will also increase, and it will cross the cracking movement, and after that the cracks which have started at the bottommost fiber of the beam section, they will start propagating towards the neutral axis. So we will say now the concrete is in the cracked zone. So earlier it was uncracked zone, now it is concrete has started cracking and some cracks are developed. So the concrete is in the cracked zone, and when there are cracks, so we can say that now concrete is unable to resist tensile stresses. So effective concrete section is reduced, which is taking the stresses. That's why we have to provide steel reinforcement so that it can take care of the tensile stresses. Now here I can just create one question for all of you, that as we have discussed, as the movement crosses MCR, then the cracks will start propagating from the bottommost fiber towards the neutral axis, and we are saying that now concrete is in cracked zone, and it will not able to resist the tensile stress. So my question here is very simple: why we are using only steel reinforcement to take care of the tensile stresses? Why not we can use some other material as a reinforcement? Why we are using steel basically as a reinforcement so that it can take care of stresses? Why only steel is chosen? So the stresses now developed will be transferred to the, and beyond this what will happen, the stresses will be transferred to the steel. So steel will start taking the tensile stresses. So here we can just try to conclude that since concrete is weak in tension, so it is assumed that all the tensile stresses will be taken care by steel reinforcement. So after that we will be saying that whatever be the section be above the neutral axis, it will be taking the, it is our assumption, it will be taking the compressive stresses, and whatever be the sectional area below the neutral axis of where concrete is still there, and that will, we will just assume that however it may take some stresses, but we will say that concrete below the neutral axis will not take any tensile stresses, only steel will take care of all the tensile stresses. Now third stage, which is very important, which we want to discuss here, ultimate strength stage. Ultimate strength stage when yielding of tension reinforcement can happen and collapse can occur. So how collapse occur and how ultimate strength reaches, so now we will discuss. Now in continuation to the previous cases where we were increasing the load, now if the load are increased further, then tensile stresses in the reinforcement and the compressive stresses in concrete will further go on increasing, and the stresses over the compression zone will become non-linear. So now we are moving out of linear phase. So compressive stresses, stresses over the compression zone will become non-linear. However, the strain distribution over the cross section is linear. The distribution of stresses in compression zone will have the same shape as of the stress strain curve in case of concrete. So stresses will be distributed, and the shape of the stresses in the compression zone will be just similar to the shape of the stress strain curve in case of concrete. Now important point is at one point particularly either the steel or concrete. Either the steel will reach or concrete will reach or both will reach their respective capacity. Then steel will start to yield, yielding will start, or concrete will crush. So either steel will yield or concrete will crush, or possibilities steel will yield and concrete will crush simultaneously. So when this happens, this is called ultimate stage or stage of collapse. Now you can see this diagram very carefully. Now we will start from this side. Now you can see, and this is a rectangular type of a beam, and this beam is supported on two simple supports, and at the bottom of the beam section reinforcement is provided. And from the top we are applying some load, and when load is reaching the ultimate stage, ultimate load, you can see here some cracks are developed, which are just like inclined type of cracks from the bottom of the beam, and they are propagating towards the neutral axis. So this will be basically cracked section at ultimate stage. Cracked section at ultimate stage. Now you can see here, and from this strain graph, strain in steel has reached, or you can say strain in steel is greater than strain in its yield strain basically. This graph is for this is for steel, and strain in steel is more than strain which happen at yielding stage. And strain in concrete has reached its maximum limit as per IS code, which we have considered in assumptions part. So it is 0.0035. So you can see here some portion which is shaded here. This is effective portion of the beam section which is taking the compressive stresses, and steel is taking care of the tensile stresses. And accordingly, this stress graph you can see here, that stress at steel will be yielding stress of steel divided by partial safety factor for steel. And similarly above the neutral axis, so this is the neutral axis, above the neutral axis you can see very clearly the stress graph is just like a non-linear type of curve, and this is the neutral axis. So this is the way how at the ultimate stage all these things happen, and how your beam section will be behaving, how cracks will develop. Now let us compare and try to understand all the three stages. Very first stage is uncracked concrete. You can see here some load is acting on the beam section. Steel is there, and the neutral axis is just looking just like at the mid of the section or towards the depth. So this is the neutral axis, and you can see here this much portion which is shaded. It is in taking care of the compressive, that is in compression zone. So accordingly there will be the strain diagram as well as stress diagram. Now this is the case when whole of the section is taking care of all the stresses. It is uncracked section. Now next stage is cracked concrete, which we have discussed. When you are increasing the load, now even in this diagram you can compare. Here load is lesser, here the load has increased. Now when load has increased, what will happen? Some of the crack will start developing at the bottom of the section. Reinforcement is there. Now when this portion of the concrete is cracked, we will say that concrete is neglected at this zone for the calculation. Now if you compare this figure at the top and the figure second figure, figure number 1 and figure number 2, effective area, shaded area of concrete which is taking compressive stresses has decreased comparatively. So area has decreased. Now it is a cracked section. Earlier whole of the concrete section below the neutral axis was also taking the stresses, but now since it has cracked, and we will be ignoring the concrete below that. So that's why we are saying that in comparison to the figure number 1, that is of uncredit section, if you compare figure number 2, then neutral axis is getting somewhat seem to be shifting upward. So here you can say the strain in the steel at this level is less than the yielding strain. And similarly, you can refer here. Still, it is a linear type of a relation in case of stress. So stress beyond above the neutral axis, it is compressive, and below the neutral axis, we are not showing any stress here because we have considered that below the neutral axis, your section is concrete, whatever we. So stress is taken by concrete below the neutral axis are ignored. So that's why only steel is taking care of all the tensile stresses. And the third case which we have already discussed, now you can compare all these three stages. And in first stage, load was lesser. In second stage, load intensity has increased. In third stage, load has reached its ultimate limit, and cracks have already propagated in the more area of the section. And you can compare figure 1 to 3. The effective area of concrete taking care of the compressive stresses has been considerably reduced. And now the concrete in the topmost fiber has reached its ultimate strain 0.0035, and here you can clearly see that strain in the steel is more than strain which is the yielding strain. And similarly, now this is the variation. Here we have considered the stress graph above the neutral axis, which is compressive stresses. So now it is a non-linear type of a diagram. So here I can create a second question, that why when we are switching over from cracked section to the ultimate stage, why the stress graph in the compression zone is taken as non-linear as compared to linear. So this is the second question, which the answer to which you can explore from the available resources of information, and just comment in the comment section. Now in this slide we want to discuss different type of failure of beam. That means what are the various type of failure which we can consider when the section is under flexure. So now let us understand the mechanism that reinforced concrete section under flexure are considered to reach the stage of failure. That means here we are talking about the failure of the concrete. When the concrete will be called as has reached at the stage of failure, when the compressive strain in concrete reaches the ultimate limit prescribed by IS 456, that is 0.0035. So that means what we want to say here, when the topmost fiber of the concrete under compression has reached to this level of strain, then we will say that it has reached at the stage of failure. Or when the steel reaches its yield strain, so then we will say that member or the section has reached at the stage of failure with the appropriate partial safety factor which we have to use as per the material requirement. So whatever be the material, accordingly when we taking care of all the partial safety factor, so then what will be the yield strain? So we will say that yield strain of steel divided by partial safety factor of material for steel. So we will say when this type of stage reaches, either concrete reaches its ultimate stage or steel reaches its ultimate stage, we will say that section is at the stage of failure. So three possibilities we can discuss here according to the failure of RCC section, which can be classified. Very first is balanced section. Now what is the meaning of balanced section? Let us understand it more effectively. A balanced RC section is one in which area of steel, that means you have provided the reinforcement in the section, when the area of steel, tension steel is such that at the ultimate limit state, the two limiting conditions are reached simultaneously. What are the two limiting which we have discussed? First limiting is this one, when concrete has reached up to this much strain and the steel has reached up to yielding strain. So what will be the graph? Strain graph. Then strain graph will be just like this. Here, as I already have discussed, the strain in steel is equal to strain at the level of yielding stress. So yielding strain divided by partial safety factor for the steel. And now you can see here the topmost fiber of the concrete has reached its ultimate strain, we can say failure strain 0.003, as well as steel at the bottom has also reached. So both the material have reached their ultimate states of failure. So that's why we will be saying that this type of failure, this type of section, when both concrete as well as steel reach their ultimate stage simultaneously, so that type of section is known as balance section. So that means in this type of section we are utilizing concrete as well as steel optimally, and this type of section will be very economical section. So already we have discussed that first stage is the compressive strain in extreme fibroconcrete reaches ultimate strain, and the tensile strain at the level of centroid of steel reaches the yield strain. So we can say here that crushing of concrete and yielding of steel occurs simultaneously. Now second type of failure of a beam section is under reinforced section. Now what is the meaning of under reinforced section? An under reinforced RC section is one in which the area of tension steel is such that as the ultimate limit state is approached, the yield strain is reached in the steel before the ultimate compressive strain is reached in the extreme fiber of concrete. So what we want to say here, that steel reaches its ultimate limit prior to or earlier to concrete. So our strain diagram will be like this. Now you can see here the neutral axis has shifted upward. Concrete has reached its ultimate strain as well as, and steel stress in steel are beyond its limit of ultimate strain. So that's mean steel has earlier reached its ultimate strain limit in comparison to concrete. Now what will happen? You can see here the effective area of concrete. Effective area of concrete, that is, this is the effective area. Taking compression decreases in comparison to the balance section. Balance section neutral axis somewhere here. So this was the effective area. But now in this case type of under reinforced section, you can see that effective area of concrete section is decreased in comparison to balance section. Similarly, you can calculate the depth of the neutral axis. So what we are saying here, the neutral axis shift upward. Neutral axis shift upward mean the effective area decreases and the depth of neutral axis has been decreased in comparison to depth in case of a balance section. So what we are going to conclude here, that during yielding of the steel, when steel will reach its ultimate stage and concrete has not reached, then what will happen? Then the bond between the steel and concrete will be just broken or weakened. So that means concrete will be getting detached, from steel, and sometime you can say elapse. That means you will get some time between the failure of steel and crushing of concrete. Now here we can consider, because steel is a ductile material. So due to ductile material, steel will not fail suddenly, and steel will be taking care of the stresses, and it will start elongating, and that's why it will not be having sudden failure. So we can say that a sudden type of collapse is not expected in case of under reinforced section. Sudden type of collapse mean Sudden type of collapse can happen only in case of brittle type of material, as we can say somewhat about concrete. Now, third type of section which is considered, that is over reinforced type of section. Now, sorry, here we have to write as over reinforced section. So you can make here some correction that it is over reinforced section. Over reinforced section is the one in which the area of tension steel is such that at the ultimate stage is reached, ultimate compressive strain in extreme fiber of concrete will reach prior to the yield strain in steel. So that means what we can say, that concrete will fail before the failure of steel, which is very dangerous, because if concrete will fail, then the whole of the you can say beam or concrete section will collapse, and you will not be able to get any signs of failure. So this type of strain diagram will be there. Here you can see here steel has not reached its ultimate strain, but concrete has reached, so concrete will start collapsing. Suddenly there will be collapse, and the effective area of concrete, we can say, taking compression increases in comparison to balance section. Neutral axis is getting shifted towards downside, and the depth of neutral axis increases. Now, very important point is, before actual yielding of steel, concrete fails by crushing. So when concrete fails by crushing suddenly without any visible warning sign, because if suppose if steel get fail before concrete, then steel will have ductility, as already told in the previous slide, and due to ductility in the steel will get some elongation, and during elongation what will happen, concrete will get detached, and some cracks may happen, and or some material may get falls. That means some of the aggregates of concrete or some of material of concrete may fall, and the people who are residing there, they can guess that something bad is going to happen. So accordingly they have sufficient time to evacuate that structure, and safety, you can say the life can be saved. So we can say sudden collapse will happen in this case without any warning sign. So that's why IS code is suggesting that never go for over reinforced section design. So code is always suggesting that you should go for under reinforced section design. So here third question is that why code is suggesting, or why we are suggesting that whenever RCC section is designed, it should be designed as a under reinforcement section. However, the balance section is more economical in comparison to under reinforcement. So question is, very first question is, why under reinforcement section is preferred, and why not a balance section is preferred? Because even balance section is more economical, and as already I have told that over reinforcement section is never recommended. So you can compare, and whatever you have learned, and you can refer some of the other sources of information, just like some standard books. As various good books are available even in the PDF format, and go through the IS 456 guidelines. And I encourage you all should ask questions and reply to the questions which I have generated in this session. So thank you. Good learning for all of you.